All right, to start, we are going to just learn some new notation here. So I'm using A and B are representing x values. And this integral with A and B plugged in here is going to represent the area between the graph of f of x and the x-axis from x equals A to x equals B. So how this might look would be like if we have a curve that looks something like that. And then let's say that this is x equals A, and let's say this is x equals B. So what we have is we have this area that's between the x-axis and the graph, and this integral is going to tell us the area of this purple shaded region. Okay, it's like the geometric area, but using calculus because there's not really a good geometry formula here because we have a crazy curve, right? So it's not as simple as just using geometry. We have to use calculus, and the calculus will help us find this area. All right, so we're going to conceptualize this and determine, I mean, this is just telling you what this integral represents, but it doesn't tell you anything about how to calculate it. So we're going to conceptualize how we actually calculate this integral that will tell us this area, okay? And this is going to be called a definite integral because it's going to give us the area under the curve. The indefinite integral is what we did before, the antiderivative, where we didn't plug in A and B, but now we're plugging in A and B, and this is going to give us the definite integral, okay? So we can start by doing a simple, so we're actually going to do one where we can use geometry and then see if that's going to help us find the calculus method, okay? So this is just a triangle, right? So the area of a triangle is base times height divided by 2. So we can see we have a base of 10 and a height of 10. So the area of this is going to be 10 times 10 divided by 2, which is just 50, right? Okay, so this is equal to 50. All right, well, what about this one? This is a base of 8 and a height of also 8. So this is going to be an area of 64 over 2, which is just going to be 32. All right? So we were able to calculate the integral of the graph y equals x, right? Because we can calculate the area under y equals x using geometry since it just forms a triangle, right? Okay, so we just did that, right? But so what about if we do the integral from 2 to 10 under y equals x? So now it's not a triangle anymore, right? Now it's actually a trapezoid. So how can we find that area? Well, there is a trapezoidal formula, right? But I'm wondering if you can think of a better way or a different way of finding this area other than using the area of a trapezoid, which is just kind of an annoying formula. All right, so think about that for a sec. Pause the video, really pause it. Okay, you didn't pause. Pause it, please. Pause the video and try this yourself. Think of a way to do this. Okay, unpausing. Now this is, you can think of this as just a triangle with this little piece cut off right here, right? So what we could do is we could find the area of this triangle, and then we could just subtract this little tiny triangle, and that will give us the area of just the blue part, right? So down here, yeah, subtract the red. That's all we're going to do. We're going to find the area of this big triangle and subtract this small triangle. So we already know the big triangle is a 10 by 10, so the big triangle has an area of 50, right? If we do this whole thing, it has an area of 50. Okay, so then we have to subtract this little piece down here, which just has a base of 2 and a height of 2, right? So it's going to be 2 times 2 divided by 2, which is just going to be 2. So the area of just the blue part then is going to be 50 minus 2, right? So we have our 50 minus 2 times 2 over 2, which is just going to be 50 minus 2, which is just 48. Subtracting the red gives us that this blue area here is just 48 square units. And what we're going to find is that there's actually a pattern within this. So we did, I'm going to rewrite this in a way that's going to seem weird, but all we're doing, because our triangle is a 10 by 10, is we're doing 10 squared divided by 2, and then we're subtracting this little 2 by 2 triangle, which is 2 squared divided by 2, giving us that 48. So there's going to be a pattern here that's going to help us round out the rest of the fundamental theorem of calculus, part 2. And yes, there is a part 1. We're doing the sequel first, which is going to seem weird, but I promise you it's the best way to approach this, I think. Okay, so We're going to try again. Let's find the area of just the blue region. Again, we're going to subtract this red triangle to find the area of just the blue. Take the big triangle minus the red triangle. So again, the big triangle is 10 squared divided by 2, right? Because it's 10 by 10. Minus, this is a 6 by 6 triangle, so it's going to be 6 squared divided by 2. So that is 50 minus 18, which is 32, right? 36 divided by 2 is 18. 50 minus 18 is 32. Okay, and the important part is just going to be the actual calculation that's occurring here, which is this. Okay, so do you see the pattern yet? Let's go back and look at our first calculation. We did 10 squared over 2 minus 2 squared over 2 for this picture. And then for this picture, we did 10 squared over 2 minus 6 squared over 2. And let's just throw one more calculation in there. If we did the integral from 8 to 10 for y equals x, that would be 10 squared over 2 minus 8 squared over 2. Again, the important thing to remember here is that this is our function. It's x. It's y equals x, right? And to find the area under y equals x using calculus, or well, sorry, using geometry actually, is we're doing 10 squared over 2 minus 2 squared over 2, 10 squared over 2 minus 6 squared over 2, 10 squared over 2 minus 8 squared over 2, right? So what is our formula here other than the geometry that's occurring here? Well, let's just look at the integral of the plane function x. Let's do the reverse power rule on this function x. So what we're going to get is that this is, well, we have to add 1 to our exponent. So it was an exponent of 1, but now it's going to be an exponent of 2, x squared. And then we're going to divide by our new exponent, x squared plus 2 plus c, right? So this is the important part. It's the x squared over 2. Because remember, when we did from 2 to 10, we did 10 squared over 2, right? Minus 2 squared over 2. For 6 to 10, we did 10 squared over 2 minus 6 squared over 2. And for 8 to 10, we did 10 squared over 2 minus 8 squared over 2. We just took our a and our b value, 8 and 10, and we plugged them in to this antiderivative, right? And then subtracted them. And it turns out that this is going to work for every function, no matter how crazy the function is. Okay? So we get our x squared over 2 plus c. So this is our fundamental theorem of calculus. If we do the integral from a to b of f of x dx, okay, what we're going to do is we're going to take the antiderivative of f of x, and then we're going to plug in x equals b, and then we're going to plug in x equals a, and then we're going to subtract them, right? And this is going to give us the area under the curve of f of x from a to b. Okay, so we're going to antiderive, plug in b, plug in a. Pause the video if you need to write this down. You don't have to write down the whole thing, but you should get the basic concept here, okay? So this will work with any curve. So we'll try it with 3x squared. Okay, from x equals 1 to x equals 4, this is our area. And it looks like it's kind of like a trapezoid, but it's not a trapezoid because this part is curved, right? Because it's under 3x squared, right? So this is not just a normal geometric shape we can find an area of. We're going to have to use our calculus here. So we're going to antiderive 3x squared, which is going to give us x cubed plus c. And we're going to use this to show that we're going from x equals 1 to x equals 4. Okay? So then to finish this now, we just have to plug in 1 and 4. So we're going to plug in 4. That gives us 4 cubed plus c minus 1 cubed plus c. So we just plugged in 1 and 4 to the antiderivative. And that's going to give us 64 minus 1. The plus c's cancel. C minus c is just 0, right? And that's always going to happen. So it turns out when we're taking definite integrals, we don't really need to worry about the plus c because when we subtract, the plus c is going away, right? But you need to remember it for regular antiderivatives, but for definite integrals, it's going to go away, they're going to cancel, okay? So our final area here ends up being 63, and that is this blue area here. This is 63 units squared, okay? 63 square units. All right, so let's try another one. Okay, try to do the integral of the definite integral from 2 to 3 of 4x cubed, which is going to give us the area under the curve of 4x cubed. If you know how to do this, you should try to do it yourself right now. If you need help, then don't pause. I will just start working through this. So this is going to give us x to the 4th by our reverse power rule. Right? Remember, we're adding 1 to our exponent, so it makes it x to the 4th. And then we're dividing by 4, but 4 over 4 is going to cancel, right? You don't always have to think about it like that. You can just kind of eyeball this and see, okay, well, I took the derivative of something and got 4x cubed. What was that something? I took the derivative of x to the fourth. Okay, so I have the derivative of x to the fourth. Okay, and I'm doing this from x equals 2 to x equals 3. Okay, so that means I just need to plug in 2 and 3 now. So I get 3 to the fourth minus 2 to the fourth, which is 81 minus 16. You can see that at the bottom of the screen too, and that gives me 65 square units. That's the area under 4x cubed from x equals 2 to 3. Okay, there's that work again typed out and not in my terrible handwriting. So we have 3 to the fourth minus 2 to the fourth gives us 65 square units. That's the area under 4x cubed from 2 to 3. Okay, pause if you need to get that down because I'm about to advance. All right, one more. We're going to do the area under the curve of x to the fourth from 1 to 2. So we're going to have to set up an integral here. We do the integral from 1 to 2 of x to the fourth dx. Okay, and so the antiderivative of x to the fourth is we're going to add 1 to the exponent, so that gives us x to the fifth, and then we're going to divide by our exponent, so it's x to the fifth over 5, and we're doing this from x equals 1 to x equals 2. So now we need to plug in, so we get 2 to the fifth over 5 minus 1 to the fifth over 5, which is equal to 32 over 5 minus 1 over 5, which is 31 over 5. The nice thing about most of these multiple choice questions is they're going to leave answers in this format, right? They'll leave it in fraction form. This is our area under the function x to the fourth from 1 to 2. So we didn't really conceptualize, well, we kind of conceptualized why this works by just looking at triangles, right? And just basically extending it and saying that it's going to work for all functions, not just y equals x, right? But we will conceptualize this further by adding context to the situation and doing functions that actually model a real-world situation. So that's what's going to happen next, but that is all for now.